Hello, Math 2318 students. I'm sure you've noticed by now that there are some instances where you have to perform Gaussian elimination by hand. You have to show the row operations and good reasons that the textbook is forcing you to do that in some of the homework problems. So this is going to be an example of showing all the row operations in order, as well as showing you then how easy it is to find the elementary matrices, which perform the same row operations by multiplying on the left. So that will come up. So these killing two birds with one stone here. Okay, so I'm sure you recognize a question like this one. It says, for which value or values of h will this system be consistent? Okay. So if you write that system of equations as a matrix equation, you get this, which has an augmented matrix that looks like this. And you can see that. That's right. Okay. Okay. So this, of course, has augmented matrix that look like this. And bad news, you can't use RREF on that because how are you going to enter? What's the calculator going to do with the variable h? So you have to perform the Gaussian elimination by hand. And that might have been that type of exercise in chapter 1, might have been one of the first instances where you had realized you had to do that. Well, there's, so I'm going to show you doing that in a careful way, using good accounting skills, for a couple of reasons that you need to be able to do that, okay? First of all, you need to know your equivalent row operations and which one to use at any given time. Doing it in the way I'm going to show you in one long column with the elementary row operations right next to each step helps you when you're trying to convert to a matrix equation involving the elementary matrices, for one. For another one, it just keeps you sane and conserves your energy to be able to get through the thing. It's so easy to make an error just when you rewrite a matrix from one step to the next, writing the wrong number. That's human error, just transmission. And then there's the arithmetic, which can happen. So if you do it in this way, it'll be a lot easier for you to track where the error happened and just correct that one step, rather than having to go back and do the whole thing all over again. Very frustrating to do that, right, after a lot of time has been spent. And also, I'd just like to point out that there are applications of using elementary row operations in things like the simplex method, which you might have seen if you took a course called 1324. Many other instances where you really need to be able to deploy elementary row operations quickly and carefully and keep track of what goes on in many applications. So here we are. On my tests and quizzes, I'll often give you some array like this with just some of the numbers missing, and you have to fill in the blanks. So knowing what you're doing is essential on that level too. All right, so now let me see if I can get rid of this glare problem. Yay, a glare problem. And give you a view of this without glare in the central places. Is that going to do it? Let's see. So the glare is here, not there. Right. Can you see that? I think so. All right. So starting with the initial matrix that we had down there, 3, negative 14, negative 3, 1, negative 6, 3, negative 1, 3, 8. Just repeating it in case you can't quite see that. All right, so you start with the first matrix, and then you follow this rule. You, for each row operation, you make another copy of the matrix, and you only do one row operation at a time. See reasons listed over here. Okay, so you're looking at this and you say, oh, I really would like that 1 in that upper left-hand corner, so I'm going to switch rows 1 and row 2. So you write that down and you do it. Notice that the things that I'm changing as I go to the new array are in a different color. Yeah, having several colors on hand when you're doing this by hand, very helpful. So we switched the 2 rows. Now what had happened next? Let's see, we wanted to turn that into a 0. So that's row 2. And using row higher, this is a good technique for imitating how a computer would be doing it. Flip that on its head. If you need to write a program that does Gaussian elimination, which you probably will at some point if you are a computer science major, and a lot of you are, it's good to start thinking in that fashion from the beginning, right? So the coding is a lot easier for you. So using 1 here, what can I multiply that by so that if I add to this I get a 0? Well, a negative 3 would be good. So what I do in a different color is I write down negative 3 times row 1. That's outside of the matrices. I write it here because in this step I'm going to take that multiple of row 1 and add it to row 2. So if I write it here in a different color, then it's easy for me to say, oh, let me add this to get that. Add to that to get this, this to this to get that. Okay. All right, so there's my new row 2. I have 1 there, a 0 there. Thinking like a computer. Computer wants to make that into a 0 as well. Computer programmed to do Gaussian elimination. Imagine this is 1,000 by 1,000 system. Would be a lot easier to proceed in this fashion. I know there's many other steps you could take. Why not take these? All right, so, oh, and by the way, in terms of the question, the homework question, for which values of h will this system be consistent? Answering that question, it is true that in a couple points along this aiming to get to a row echelon form down here, there's a couple points we could have just, as a human, we could say, oh, well, to answer my question about whether the system is consistent, I don't need to keep going here. But you see, that's not our primary goal in this video, in this lecture. I want to show you what it looks like to do Gaussian elimination by hand for a number of reasons, killing off a number of different instances where you're going to need this skill. So yes, it's true that at some point we could just pop over to a system of equations and solve that section 1.1 or 1.2 homework problem. Very true. But anyway, let's keep going. Let's get this into at least row echelon form. All right, so we need to get rid of that 1. What's going to do it? Well, if we could add this 1 to that one, that would make a 0. So the row operation is that the new row 3 should be equal to the old row 3 plus 1 times row 1. And notice I didn't have to write that down because 1 times row 1 is sitting right there, right? Or here's a copy right here. So adding these two together, these is what I get to do when the scalar, in that third row operation type, when that scalar is just 1, it just feels like you're just adding 2 rows. All right, so we get this third row. Okay, now we've started to affect this expression with h. Got to keep good track of that. Is it in row echelon form? Notice I'm not even talking about RREF, just REF. Not yet. I need to get a 1 here and a 0 there. All right, so yes, Yes, to answer that one little question, for which value of h will the assistant be consistent, I could pop into system of equations now and find a condition on h. But just for these purposes, stick with it. All right, so we're keeping on going. Let's lower this. Trying to make a 1 happen here. That means I need to take row 2 and multiply it by 1/4. And I did that and disobeyed my own rule, writing that in a different color. So let me fix that. Okay, and I got from here to there by this operation, keeping careful track of how you denote where these, the operation is between what two matrices is careful, is worth your time being careful so that later you can pick it up easily. All right, now what do we need? We need to make this into a 0 to get into row echelon form. So 3 times that added to this would give me that 0. So 3 times row 2 is what I need. I write it down here in a different color. And my row operation is that new row 3 should be equal to old row 3 added to 3 times row 2. I write it right there, then I can just add those together to give me this last row here. 0, 0, and -3 plus 3 gives me a -6 plus h, also written as h minus 6. And you can see that. Okay. So we are done as far as getting into row echelon form. It's not reduced row echelon form because that -6 is still there. It's not a 0. But this is sufficient for answering our question and allows me to show you a nice array of several row operations one after the other. Okay, so we're going to come back to this and rewrite it as a system of equations in a second and answer that one particular homework problem. But before I leave this, let me show you how to come up with the elementary matrices that perform each of these row operations. Doing them in parallel with this makes it really easy. So to make an elementary matrix, remember, all you have to do is take a row operation and perform it on an identity matrix of the correct size. Just want to make sure you guys can see all that. Not easy. Not easily. Oh, that looks so light over there. All right, so the thing to remember about elementary matrices, I'm doing them alongside this, but I'm not doing the same thing I did over here, where I perform row operation on the previous, row operation on the previous. That's not happening here. For elementary matrices, to generate them, you take each row operation and perform it on an identity matrix. So this one gets performed on that, this one on that, this one on that. Okay? So that's why I have all these lovely, well, ugly looking lines here to emphasize they're not in a chain, one based on the other. They're all coming from the identity matrix. So how do you switch 2 rows? You multiply by an elementary matrix where you switch 2 rows in the identity. How do you replace row 2 with itself added to -3 times row 1? You multiply it on the left by an elementary matrix where you did that to the identity. -3 times row 1 added to the old, -3 times row 1 added to the old row 2 would give you this. We had another video we talked about why these elementary matrices perform those operations. So here I'm just talking about how to calculate them quickly. All right, third row operation was this one. See how it's nice to have the accounting? You just pop right in here. What is that? New row 3 was equal to old row 3 plus 1 times row 1. You'll notice, well, I should have written that in red. Right, every time I did that third type of row operation, this with the -3, this with the 1, this with a 3 here, those scalars appear in their elementary matrices in particular spots, okay? So the -3 that we multiplied by row 1 and added to row 2 is appearing in the 2, 1 spot. Hopefully you remember from your reading that each matrix has, each entry in a matrix has an address. So this is the 2, 1 spot because we're in the second row, first column. This one should appear where? Well, let's see, it should appear in the 3, 1 spot, right? Because we're changing row 3 by adding a multiple of row 1 to it. And sure enough, there it is. This one should appear in the 3, 2 spot. And it does, right there. Okay, so apart from those additions, this one, and this one are just elementary, just identity matrices. What does that second type of row operation where you multiply by a scalar multiple look like? How does that change things? Well, you'll notice that scalar is in place of the one on the diagonal of that row. Right? So you either swap rows in the identity, put in that scalar in a special spot, or change the 1 out for that scalar if you're doing the second row operation. Okay, so that's some practice generating elementary matrices, excuse me. I just want to emphasize why we do that kind of thing down here at the bottom before I go back to that other question. Okay, so we had AX equal to B, we had A, B augmented matrix, it became A prime, B prime, right? Over here we generated some matrices, EI, E1, E2, E3, E4, E5. Notice how we would have used them in a matrix equation. AX equal to B, the original system, we would have multiplied it on the left by E1 at first, then multiplied that result by E2, then multiplied by that result by E3 and E4 and E5, getting this equation. So what is this augmented matrix, what does the last augmented matrix look like? It has this A prime, which is a product of these 6 matrices, equal to product of these 5 matrices multiplied by the original B vector. That's what A prime X equal to B prime really is. Good to know. Well, let's get back to picking off the answer to that homework question which forced you to use Gaussian elimination and not use RREF in the first place. Let's see, where a good spot would have been to jump in and solve that one. Well, we could have done it right here. But since we've done all this work, why don't we look at this line right here? Okay, so look what that line is saying. This was an augmented matrix for this system over here. So going back to the original notation, right? So this last line has become something that looks like 0x plus 0y equals h minus 6. Right? 0x plus 0y is equal to h minus 6. Well, that means 0 is equal to h minus 6, right? And that implies, lo and behold, h is equal to 6. So now you can go back and answer that question. Original question, for which values of h will the system be consistent when h is equal to 6?